So today we're going to finish up with peptides and proteins. We could actually spend the rest of the semester on it. It would be awesome, but we won't. We were talking about solid phase peptide synthesis. Last time we introduced protecting groups to you. And we also introduced to you the Merrifield solid phase resin method, where we have a polystyrene bead or set of beads, each of which has multiple chloride functional groups on them. And we talked about how we can load an amino acid as a carboxylate onto the resin in an SN2 style reaction. That creates an ester linkage. Now that ester linkage is not permanent because we know how to break esters apart, but it's stable to a lot of the conditions that we might use for solid phase peptide synthesis. And we talked about how having the amino acid linked to a resin bead is like putting a macroscopic handle on a molecule that you can literally scoop it up out of a solution, move it somewhere else, and do something else to it. Really, really useful. It also makes the purification required after each step of a synthesis much more easy to do. So we talked about how the Bhakti protection would be using a really strong acid like trifluoroacetic acid. These conditions aren't really aqueous. They have a small amount of water, so there's no danger of hydrolyzing this ester. But the Bach group is removed under these acidic conditions, like I showed you last time, and you can see the mechanism for that in the notes from last time. Importantly, this reaction happens in 100% yield, and it's really easy to isolate the product, which is the deprotected amino group on the resin. You do this using this sort of experimental setup. Please don't memorize that or even draw it. It's just an idea of how we do this in the lab. Here's the solution of TFA and water. Here are your resin beads. There's a little stir bar, and there's a filter at the bottom that you can use when the reaction's done. Of course, when the reaction's done, what you want is on the bead. So you can simply drain everything else and isolate the bead and carry that on to the next step. You'll rinse the resin several times because you wouldn't want any remaining carboxylic acid to be around to interfere with the next step of the reaction. So that's the deprotection step. Having unmasked an amino group, you are now ready for the next coupling reaction. By the way, this resin-bound amino acid, we don't need to worry about the C-terminus because it's tied up, basically protected as an ester with the resin or the polystyrene bead, which we often call the resin. So the coupling step is just what you would expect for an amide bond reaction. Only because of the solid phase synthesis setup, we are able to use a vast excess of one reagent over the other. So typically, the limiting reagent is our amino acid on the polystyrene bead. And then to drive the reaction super to completion, we use 4 or 5 excess equivalents of the next amino acid we want to couple on. So 5 moles of DCC and 5 moles of amino acid for every mole of resin-bound amino group. Your solvent here is DMF, which I've drawn the structure for you there. You don't need to know that structure. It's just a polar solvent that is good at dissolving amino acids and DCC. Typically with this, we also include an equivalent, we also include a non-nucleophilic base like triethylamine, because the mechanism is going to involve removing a proton from the next amino acid, having that carboxylate then attack DCC. And you can refer back to the early chapters. I think it was chapter 16 where we introduced DCC as a reagent. That makes the next bond between the carbonyl carbon of this next amino acid, which I've highlighted in purple, and the amino group of the green amino acid that's bound to the resin. That new bond is highlighted in red. And this next amino acid that we're using is also Bach protected on the nitrogen to avoid the problems that we've talked about. When the reaction's done, hopefully we've got almost 100% yield of this now dipeptide. we're still going to have in solution the remaining 4 equivalents of amino acid and DCC, but because we're on solid phase, it's trivial to remove all of that. We simply drain the solvent away. We keep the beads. We rinse the beads several times with some solvent, and then we're able to move on to the next step. If you were to do this in solution phase and use 5-fold excess of the next amino acid, you would have a problem at this stage because you would have to try to separate your dipeptide from the 4 moles of other amino acid that you have. And that can be challenging. The fact that we're doing this on solid phase makes this as easy as it only takes as long as it takes to drain the solution away from the beads, and that's usually pretty quick. So that's a deprotection step followed by a coupling step. Overall, those 2 steps removed Bach and put on the next amino acid. And so for every amino acid that you want to add to a growing peptide chain, it takes a coupling step and a deprotection step. And from that point on, it's pretty easy and even boring. In fact, Merrifield used an elaborate system of pumps controlled by electric switches to automate the process. It's now, any number of companies will now sell you for $100K or so a peptide synthesizer where you supply the amino acids and the reagents, and it does all of the liquid handling for you. We still actually do this process by hand in my lab because anyway, for reasons that we don't need to get into. But now you can, some of you are scared of coming to an exam and seeing the question that says, synthesize the following peptide via the Merrifield method. And you're afraid of seeing a large peptide with the following sequence. Or something like that. And what you need to know is, your first step is, you've got to load the C-terminal amino acid on the resin. And then steps 2 and 3 are Bach deprotect. Step 3 is couple the next amino acid. What do we mean by next amino acid? When we're making a peptide via the Merrifield method, we start at the C terminus, and then we go from C to N, coupling on each successive amino acid. And after you've coupled the next amino acid, you go back and you Bach deprotect, and then you put on the next amino acid and the next. It's iterative in this way. So it's actually not hard to write out a synthesis for a solid phase. Okay? Questions about that? Yeah?
Is it just assumed that protecting groups are on everything?
Yeah, so one of the things that I've done here is not limit myself to the side chains that don't have groups that could interfere with things. You're gonna, as I've written here, all of the amino acids that you couple on would need to have an amino protecting group like Bach. Some of the amino acids are going to have side chains that would need to be protected too. We haven't covered that in the class. We're going to ignore it. But it's something that's not actually that difficult to deal with. One thing we haven't done, another hand, yeah?
Yeah, so we use Bach or FMOC.
Could you use Bach or FMOC? Yes. And I'm going to show you why you'd want to use FMOC in just a second. Yep. So one of the things we haven't done is, suppose you get to the end of your synthesis and you've got your peptide now bound to the resin at the end. And then we're going to say that I'm just going to put a carbonyl here, and then we're going to copy our disclosing my secret identity. I guess the fact that the costume is still sitting in my office is a dead giveaway. Okay, so you do the last coupling reaction, and you want to now remove your peptide from the resin. After the final coupling reaction, probably, depending on what you want, but usually you're going to do, and I'm not sure what step to call this. We'll call it step, I don't care, N. You guys probably hate that. Step N. I know, let's go really mathy because this is not the last step. Let's call it the N-1th step. How's that? Bach deprotect. We're going to remove the final Bach group. That's using 95% TFA and water, which is great. What's that going to give us after that step? Well, the N-terminus will be the free amino group rather than the Bach protected amine. So I'm going to go ahead and erase the Bach group and replace it with just the amine. Now our next step, step N, is to cleave the peptide from the resin. And it might be useful at this stage to remind ourselves how the peptide was attached to the resin in the first place. And it was something like this. So one of the benzene side chains of polystyrene has a CH2 group on it, and then that CH2 group is attached to one of the oxygens of the C-terminal carboxylate of our peptide. Basically, our goal is going to be to break this bond. And Merrifield's method, the best way to do this was basically through a competing SN2 style reaction. You use hydrofluoric acid, which is not actually a very strong acid. As you know, HF has a pKa of around 4. If you didn't know that, I just told you. You don't have to have that memorized. So it's not that strong of an acid. What's probably happening, though, is the fluoride of HF is doing an SN2 reaction here, replacing the oxygen at the benzylic position with the fluoro group. We won't worry about that in any level of mechanistic detail, but when we're done, the peptide is free from the resin. What you probably have over here, though that probably doesn't matter too much, is the fluoro version of your resin. Now, if you don't know anything about HF, you should consider yourself lucky. It's a challenging reagent to use. You can use it to etch glass, which is kind of fun, but it's also highly dangerous. If you get it on yourself, it's not dangerous in the acid sense. It's not any more really acidic than vinegar, but the fluoride ion itself, HF, can actually damage your bones and you can die from it. So if you ever use HF, you have to take special precautions. There's some antidotes that you can have on hand if you get exposed to it. And the people that use it all the time say it's not really that big of a deal, but they do have to have special equipment to do it. And so there was this need 20, 30 years ago among people that wanted to do peptide chemistry but were scared of HF. And by scared, we're not only talking about the chemists doing it, but we're talking about the institutions that support the chemists who are afraid they're going to get sued if somebody gets hurt using HF. So chemists were pretty inventive, and they came up with an alternative resin linkage that is more effectively able, which you can cleave under conditions that don't involve HF. So what I've shown you there is the Merrifield method. What I'm going to spend maybe 5 more minutes on is an alternative strategy for the peptide resin linkage. And you're going to see that when we change the peptide resin linkage, we're actually going to need a different protecting group for our amines. So Merrifield, well, others, let's see. Let's start with the polystyrene bead, the benzene side chain coming off of it. And in Merrifield's resin, it was a chloro group, right? Chemists figured out that if they attached the following group, that actually dramatically changed the properties of the resin. For reasons that don't immediately look obvious, but basically, to understand why this changes the properties of the resin, I need you to think about the relative stability of the following two carbocations and what you know about resonance electron donating groups versus withdrawing groups. Which of those two carbocations do you think is more stable? Any ideas? Which is the better electron donating group? The methoxy group is a better electron donating group. And actually, you should be able to see how by resonance, I can stabilize the positive charge on the benzylic carbon using lone pair electrons from the oxygen. And it just so happens that even though on the right a methyl group is also electron donating, it can't donate electron density via resonance. Okay? So, having a methoxy group para to a benzylic carbocation stabilizes the carbocation. You got that? That is important. Otherwise, you will not understand the shenanigans that are going on here with how we change the resin. Okay. So, keep that in mind. We're going to shrink it and put it over here. Now, in Merrifield's method, we're going to load an amino acid. I'm sorry, we didn't shrink everything. I'm now being distracted by the non-shrunk words. There we go. That makes me feel better. This is a modified resin. It's still basically the Merrifield resin, but it's got this new linker on it. And the new linker I'm going to highlight in pink. And the key features of the linker are we still have the benzylic chloride that's a leaving group, but now we have this para, it's not a methoxy group, but it's this para alkoxy group that can act as an electron donating group. So imagine what happens now when we load our peptide onto the resin. Oh great, we lost the highlighting, how sad. We're going to load it onto the resin via the same SN2 reaction that we did previously. I don't like that bond angle, but we're going to tolerate it. Okay? We'll see about that, actually. I can't tolerate it. All right, there we go. So previously, with the regular Merrifield resin, we needed to break this ester, we needed HF so that fluoride can do an SN2 reaction. Now, because of the stability of this resonance stabilized carbocation, this bond is basically what we're going to call SN1 labile. The carbocation is stable, so all we need to do is turn this carboxylate into a good enough leaving group and it'll leave on its own. The reagent of choice for that is trifluoroacetic acid, or TFA. And what happens is that the TFA, CF3 carboxylic acid, protonates the carbonyl oxygen, like you would expect an acid to be able to do, okay? I'm now gonna, rather than redraw everything, I'm gonna erase the arrows and show you what you would have after the protonation step. Oops. Now it's perfectly fine for these electrons to just leave with this oxygen, kick down to form a pi bond, and then break the pi bond to make the carboxylic acid. When that happens, we've got our Darth Vader peptide now. And at its C terminus, we have the carboxylate. And then what's left over from the resin is exactly this resonance stabilized carbocation situation that I told you about. And hopefully you can see, we're not going to redraw those resonance structures, but hopefully you can see the relationship between that para-alkoxy group and how it can stabilize that positive charge by resonance. Okay? So TFA is still not a very safe reagent, but if it's corrosive, if you get it on your skin, it will burn you, but you're not going to die that day, whereas with HF that could happen. So, safer, right? What is the problem with using TFA to cleave the linker between the resin and the peptide, given the strategy that I've told you about so far? What is the huge problem? Go ahead.
You also use it when you remove box.
Right, you also use it when you remove box. So if we use this strategy unchanged, we load our amino acid on resin, we go to do the first Bach deprotection, and sound effects, the amino acid pops off the resin, and you're done. Terrible idea, right? So if you want to use this safer way of cleaving your peptide from the resin, you cannot use Bach as your strategy for protecting the nitrogen. You understand that? So we need an alternative, and it would be great if the alternative was stable to the conditions of the coupling reactions and stable to TFA, but not and cleavable under a separate set of conditions that aren't going to influence the resin linkage. So that's why we're going to come back to this strategy requires a new amino protecting group. You've read about this in your text, so I'm just going to introduce it to you now. We'll talk about it briefly, and then I'll show you how it fits in. That new protecting group is FMOC. Nobody says FMOC, okay? So you can try, but people will look at you funny if you do. FMOC, okay? So like Bach, it's going to have, here's your amino acid, here's your carboxylic acid group. Like Bach, it's going to share the carbonyl carbon and an adjacent oxygen, but instead of having a tert butyl group here, it's going to have this weird structure. A 5-membered ring, and I know how much you like polycyclic ring systems. Okay. For strange reasons that are not important, this type of hydrocarbon, 2 benzene rings linked via a 5-membered ring with an additional carbon, is sometimes called fluorine, not to be distinguished from fluorine, FLOR, whatever, INE, the element. I don't know why it's called that way. I didn't make it up, but that is where the F comes from. So fluorine is, I guess I drew my line too long. Fluorine is just the rings. This M is for methyl, like a 1-carbon unit. O is for oxy, and C is for carbonyl, or FMOC. FMOC is acid stable, can resist deprotection indefinitely in acidic environments, but it is base labile. And I'll show you how that reaction happens. So here I'll redraw the FMOC protecting group. Here's the 5-membered ring. Here's the second benzene ring. Methyl oxycarbonyl nitrogen, and then some R group there. Under basic conditions, and the standard conditions are to use this secondary amine base that's called piperidine. Lone pairs on the nitrogen remove this proton. There is a reason that proton is relatively acidic and removable, and the fun answer is, well, the reason why you should be able to answer based on what we talked about in a recent chapter. So ask yourself now, looking at that anion, is it fully conjugated? And how many electrons does it have? 2, 4, 6, 8, 10, 12, 14, and that satisfies the 4n plus 2 rule. So this anion, the conjugate base of the fluorine segment, is actually aromatic. That's one of the reasons why you can remove the proton. Once it's removed, you should see how we're pretty close to doing a decarboxylation. Electrons kick down to form a new pi bond. Electrons here go to form the CO2 pi bond, and then these electrons pick up a proton from some source, possibly the conjugate acid of our base. What that does is that generates the following pieces. This piece is now called dibenzofulvene. You don't need to know what that is, but it's actually, you can see it by UV vis spectroscopy. And sometimes people monitor the appearance of this group as evidence for FMOC deprotection. CO2 leaves, and then over here you've got your amine. That's the deprotection mechanism. Your text will show you how you can install an FMOC group. It's actually pretty easy. You start with an amine. You need a non-nucleophilic base like triethylamine. And then the reagent for doing this is actually pretty simple. There are a couple of them that work, but this is called FMOC chloride. And it's basically nucleophilic acyl substitution. That is, you're going to have nitrogen attack the carbonyl carbon, get a tetrahedral intermediate, base will assist with proton transfer, and then the chloride leaving group gets kicked off. That's how you install the FMOC group. And of course, the product from that is going to be, you can write just like this. That solves our problem for using this sort of altered solid phase peptide synthesis strategy. We can use the acid labile linker, but instead of using Bach protecting groups all along the way, we'll use FMOC. Does that make sense? So I'm probably not going to draw that out for you. What you would need to do is go back here and realize that if you use this new linker that has an acid labile linkage between the C-terminal amino acid and the resin, that you will need an amino protecting group strategy that involves FMOC instead of Bach. So up here at this stage, when you were using instead of Bach deprotection, you'd use FMOC deprotection, and the conditions would be you'd use that base, piperidine, to do the deprotection. Okay, I feel like your text talks about that in a fairly decent amount of detail. Any more questions you have on that? Yeah.
Is there a reason that we don't just use hydroxide to kick off the entire recipe?
Is there a reason you don't use hydroxide to do what?
To do,
Oh, to cleave from resin? That's a good question. Why not just saponify the ester using hydroxide? There's possible, I don't know. They must have tried it and it must not have worked very well. I don't really have a good answer why. It's a good question. Okay, others? So in my lab, most of what we do is the FMOC strategy. I've never actually done the hydrofluoric acid procedure, mostly because, again, people that do it say it's not that big of a deal, but you have to have a special setup to do it. So, all right. The last thing we want to do in this chapter is give you a sense of why amino acid side chains are important by considering what the atoms are doing in an actual enzyme active site. So we're going to take a close-up view of the active site of a class of enzymes called serine proteases. Serine is the name of an amino acid, and in a serine protease, the side chain of a particular serine is really important for the reaction. So proteases cleave amide bonds. And in your text, I think in this chapter, I've had you read some things about enzyme names so you can get a sense for what enzymes do. Proteases cleave amide bonds in proteins. So the active site within a serine protease has something that has come to have been called a catalytic triad. There are 3 amino acids that are important for hydrolyzing the amide bond. Now let's just look at an amide bond. We've told you before that amides are really stable, and that is because NHR minus is a terrible leaving group, and because the amide nitrogen lone pairs are donating electron density into the carbonyl carbon via resonance and making it not very electron poor. We have learned before in chapter 16 how to hydrolyze amides, but you had to cook them in either really strong base, OH minus, or really strong acid, H3O plus. And even then, the reaction is pretty slow. You can tell that the reaction is pretty slow because your cells and your body is full and made of a lot of proteins, and the amide bonds are not being rapidly hydrolyzed, at least not in an uncontrolled fashion. So you really do need an enzyme to accelerate this process. Now think of the problems that I told you about. First, the carbonyl carbon is not that electron poor. Second, the amide nitrogen is a terrible leaving group. So if you think about what the task of this enzyme is, it's going to be to make the carbonyl carbon more electron poor and to make the amide less of a cruddy leaving group. So let's talk, and a lot of the times the way enzymes do this is through hydrogen bonding and proton transfer. So a couple of things to know about the active site of a serine protease. Not part of the catalytic triad, but really important, are a couple of amide bonds from amino acids that we don't need to necessarily worry about which ones they are. So I'm just drawing a couple of amide bonds, and those are hydrogen bonding with the carbonyl oxygen. Why might that make the carbonyl carbon more electron poor? Any ideas? What do you think? Anybody want to commit? Go ahead.
Because you're pulling electron density away from the oxygen, and the oxygen is what's trying to pull it away from the carbon. So it's like
Good, yeah. So you can think of this alternative resonance structure for a carbonyl, where the lone pairs are out on the oxygen. Oxygen's more electronegative than carbon. Hydrogen bonding should stabilize this anion, right? And to the extent that we can stabilize a buildup of negative charge on this carbonyl carbon, we can make the carbonyl oxygen, we can make the carbonyl carbon more electron poor, okay? Good. The other thing that's going to do is remember what a tetrahedral intermediate looks like. It has a negative charge on that oxygen, so the hydrogen bonding stabilizes the negatively charged tetrahedral intermediate. You'll learn about this when you take biochemistry. This setup of hydrogen bonding is called the oxyanion hole. It's a little pocket that the carbonyl oxygen sticks into with hydrogen bonds in it that stabilizes it. Okay, second thing we need to worry about is how do we handle the proton transfer? And we need to get a good enough nucleophile to attack this carbonyl carbon. So enter the amino acid side chains. One is this serine amino acid. I need to draw it a little bit differently. That'll work. So that's serine. I'm just drawing the beta carbon and the OH group. Next to that serine amino acid is a histidine. Histidine has this imidazole side chain structure. Oh, how horrible. They've drawn it incorrectly in the text. I can't even stand that. This is histidine. All right, and then next to the histidine is an aspartate, which again should have this basic side chain structure. So in each of these cases, the squiggly line indicates the bond between the beta carbon of the side chain and the alpha carbon of the backbone. Serine, histidine, and aspartate are the catalytic triad. So it's thought that what happens is a cascade of proton transfer events. Negatively charged oxygen removes a proton from histidine, which adjusts and in turn removes a proton from serine, which at the same time becomes negatively charged and attacks the carbonyl carbon. All of that happening in what appears to be the same concerted step. There's tons more we could talk about here, but we're going to just go through it in this level of detail, and then when you learn more about it later, you can be even more surprised and awe-inspired. So now, I'm going to erase the arrows. If you followed what we've done, we have a new bond between the oxygen of serine and the carbonyl carbon. I'll illustrate that new bond in blue. The carbonyl oxygen is negatively charged now. The proton from serine is now attached to histidine. And the proton from histidine is now attached to aspartate. And I'll draw that proton in blue as well. Okay, so that proton moved over, that proton moved over. At this stage, we've got a tetrahedral intermediate. Lone pairs on the oxygen can kick down. They're going to kick off this amino group. As it's leaving, it's going to take the proton from histidine. Because remember, if this left is a negatively charged NHR minus group, that's a terrible leaving group. So we remove the proton from histidine. At the same time, histidine steals its proton back from aspartic acid. And that allows us to reset with the following intermediate. I'm going to stop drawing the oxyanion hole as I've done previously. You're just going to have to imagine it there. Your carboxylate group from the amide bond that you're hydrolyzing, we've now converted that from an amide to an ester. The amino group is now free to go off and leave the enzyme active site. And then what we've got over here is our restored and regenerated histidine and aspartates in their original state that they were to begin with. Okay? So that's the first half of this reaction. It's in your text. I'm not making this stuff up. By the way, when you eat protein and your stomach digests it, this is what's going on. The enzyme chymotrypsin is doing this right now inside you, so it's kind of important. All right. Do you want to see the second half? Questions about the first half? Go ahead. Right. Could you theoretically replace aspartate with glutamate? I'm sure someone has done that experiment. We don't think it works that well, and the reason is that these side chains have to be really close to each other, almost touching. In fact, it's unclear sometimes whether this hydrogen belongs to the histidine or to the aspartate. You might imagine extending that side chain out by one additional CH2 unit might position it in the wrong place. We could look it up and see, has somebody swapped out aspartate for glutamate and is the enzyme as efficient? The answer is they've probably done it and it's probably not as efficient, but I don't have the data. Yeah, what else? Okay, well, the second half of the reaction is going to be exactly the same as the first, only our goal now, instead of getting rid of an amide, is going to be to hydrolyze this ester. Fortunately, esters are easier to hydrolyze than amides, and our nucleophile is going to be water. So we're going to take this same, we'll just move the amino group up here. We'll say that it leaves the enzyme active site. Water comes into the enzyme active site. And again, it's going to be positioned so that aspartate steals a proton from histidine, which steals a proton from water, which then attacks the ester as hydroxide, giving a tetrahedral intermediate that looks like this. Oops. And then electrons are going to kick down. Serine's going to leave. It's going to steal a proton from histidine, which is going to steal a proton from aspartate. That's going to release the carboxylic acid, which now can leave the enzyme active site. And that's going to restore the catalytic triad to its initial state. That's really important because, as you learned in Gen Chem, perhaps even in high school chemistry, catalysts are left unchanged by a reaction. So once the reaction's over, we need to be set to go in the active site with all original side chains, and indeed we are. Okay? So if you follow what's happened, we've used the aspartate and the histidine as proton shuffle reagents to deal with all the proton transfer reactions. Okay, any questions about that? Yes?
Do the pKa's of those amino acids influence where it's attached and stuff at all?
Yeah, so what role does the pKa of these individual amino acids play? It's actually, I'm glad you asked. We don't have time to answer it in a huge amount of detail, but let's just consider this. The pKa of this serine proton in the first step is about 16. My phone now thinks because I said serine that I was saying Siri. How about that? No, I was not talking to you. Thank you. What is the pKa of the conjugate acid of histidine? Do you remember? 6, right? So should the histidine neutral whose conjugate acid has a pKa of 6, would you normally expect it to be able to remove a proton whose pKa is 16? No, that's like 10 billion times ineffective. Similarly, let's consider the pKa of aspartate, or aspartic acid, the conjugate acid of aspartate. It has a pKa of around 5. Do you expect its conjugate base to be able to deprotonate histidine, pKa 6? Maybe to 10% level, right? But normally the strongest acid loses its protons. So there's sort of a mismatch in pKa's, and one question that people have asked is, how does that work? The answer is, first, the pKa's that we've measured for these side chains we did in bulk aqueous solution out in water. The enzyme active site is somewhat sequestered from water, and the absence of water changes the pKa's. The other answer is the fact that these side chains are held so close together probably also alters the pKa's. And then there's an alternative explanation about the fact that this hydrogen is probably shared pretty evenly between the two the nitrogen and the oxygen of histidine, the oxygen of aspartic acid. There may be some quantum effects going on, something called a low barrier hydrogen bond, but it's something that people are thinking about. For us, though, as we talk about biochemical reactions in the future, we're often not going to look at an enzyme active site in this level of detail. You will do that in 481. For our purposes, a lot of times we'll just show a generic HA or a generic B doing the proton transfer, but I want you to understand the kinds of functional groups that can do this in enzyme active sites. Okay, so that's it for chapter 23. Now, as I look at my schedule, we were intending to be done with chapter 24 today. So good luck with that. Next time we will know. We're going to go ahead and do chapter 24, which is on carbohydrates. We will spend probably one to 1.5 lectures on that and then move on to lipids. In the remaining couple of minutes, then, let's introduce some carbohydrates. One of the best ways to disillusion an audience next time you give a sacrament meeting talk is when there's about 5 minutes left in the meeting and you're still going on for your 30th minute, you then say, now in the second half of my talk, I would like to, actually that's best deployed in a state conference when it's plausible. So if you ever have to talk in a state conference, try that one out, see what happens. Carbohydrates. To some extent, this is going to be nice and review-like because you've already done a lot with cyclic hemiacetals. There are 3 carbohydrate structures I want you to know because there are sort of 3 6-carbon carbohydrates that are really important in biology. Glucose, mannose, and galactose. And all 3 of these are going to have closed chain cyclic forms and open chain aldehyde forms. Glucose is the easiest because if you draw it, everything except maybe carbon 1 is equatorial for reasons that we'll talk about. That's glucose. Then you can remember the structures of mannose and galactose by saying in mannose, carbon 2 is up, axial, and in galactose, carbon 4, the OH group is up, axial. In other words, mannose and galactose are diastereomers of glucose where one and only one stereocenter has changed. Okay, that's it for today. See you on Wednesday.